Hello, welcome to lecture 24. We will continue seeing applications of Chebyshev inequality. But these applications, they are important in themselves. But in addition, they are chosen so that you see how to handle the case when there is no pairwise independence and there is serious amount of covariance. Remember that we are still thinking about studying a random variable x by decomposing it into a sum of easier to analyze random variables like x is equal to x1 plus x2 plus xn. If there was pairwise independence among the summends, we could use the formula that the variance of x would be sum of the individual variances. But if there is no pairwise independence and there is non-zero covariance between them, we will have to we'll have to somehow tackle them. Okay, and the problem with covariance, as will be illustrated shortly, is that there are quadratically many covariance terms compared to only linearly many variance terms. So taming the covariance and thereby bounding the variance of x is sometimes tricky, but there is a very a technique with a wide applicability. We will first see that technique in this example of phase transitions, and then we will make a general remark about what is the underlying technique. Okay. By the way, this application is important not only for to seeing this way to tame the covariance, but in itself this is an important insight that probability theory gives to physics or statistical physics in the notion of phase transitions that you have seen when ice turns to water or water turns to steam, right? So there are similar phenomenon happening in combinatorics. That's why this is called a phase transition, but I'll speak more about that after we see what does probabilistic method give us. Okay, so this is the setting. We sample a graph G according to G and P. Okay, so remember that G and P is a probability distribution where you construct an n-vertex graph by independently picking each of the possible n-choose 2 edges with probability P. Okay, we have seen this many times before. And what is the question we are interested in? We are asking the question, what is the probability that what is the probability that G contains? We are asking the probability that G contains a copy of K4. Okay, so it's easy to guess that this probability will depend on P, right? If P is very large, then we are constructing a dense graph, and hence it's very, very likely to contain a K4. Whereas if P is very small, then it's less likely to contain a K4. So most of the time we will choose this P to be a function of n. Okay, you will see the reason why. So it's valid to think about P as a constant. Like you can ask, what is the probability that G of n comma 0.5 will contain a K4? But it will turn out that if you put a constant here, then for large enough n, the answer would just be 1. It will almost surely contain a K4. Okay, so we are to get a more finer understanding, we will work with P being a function of n. But hold on. Okay, you will see the motivation once you go through the solution. Okay, so how do we attack such a problem? How do we estimate the probability that G contains a copy of K4? So let's set up a random variable x which counts the number of K4s in G. Okay, why do we do that? Because this is now x is easy to write as a sum of smaller random variables, or easier to analyze simpler random variables, let me call them, where you pick for each 4-sized subset of vertices, or each set of 4 vertices, you define a random variable xs, right? This we have done many times. For each set of 4 vertices, your xs will be 1 if this induces a K4, which means all the 6 edges are present, and it will be 0 otherwise, right? So xs is 1 if s induces a K4 and 0 otherwise. So x is now a sum of n choose 4 such random variable. Okay, each 4-size subset of the vertex set of G, which is n, gives you a random variable xs. What is the expectation of xs? It is nothing but the probability that xs is equal to 1, because this is a indicator Bernoulli random variable. in fact a Bernoulli p power 6 random variable, right? Because the probability that xs is 1 is p power 6 because all these 6 edges have to be present, and that is also equal to the expectation of xs, and hence the expectation of x is n choose the sum of all these things. Since each term is p power 6, we get n choose 4 times p power 6, or if you ignore the constants, then order of growth of this is n power 4 p power 6. This is the expectation. Okay, now you will see the see why I blabbered about choosing p to be a function of n, because if p is a constant, let's say even if it is like 1 by a million, it's a very small constant. For a very large value of n, this ex goes to infinity. Okay, whereas if I kind of play a bit more with p and allow p to be a function of n, as it is shown here, allow p to be a function of n, then I can get something more interesting. I can get what is known as this phase transition, to be more precise. Okay, so now if you play with this n power 4 p power 6, right, you can determine what is the growth rate of p such that this n power 4 p power 6 will vanish, go to 0, and what is the growth rate under which it will go to infinity. Right, these are the two distinctions that we want to make. Okay, so you can actually try to solve for that by checking when is this strictly less than 1 and when is it strictly greater than 1, right? So you will see that this means p power x is strictly less than n by 4. So p cube taking square root is less than n squared, or p less than n power minus 4, because n power 4 goes to the denominator, n power minus 2 by 3. Okay, so if p is little o of n to the power minus 2 by 3, right? What does that mean? That actually means p divided by this n to the power minus 2 by 3 goes to 0 as n tends to infinity. That is what the definition of little o means. Similarly, omega means p by n to the power 2 minus 3 goes to infinity as n tends to infinity. So depending on whether p is little o of n to the power minus 2 by 3 or omega of little omega of n to the power minus 2 by 3, this expectation has a very different behavior. In the first case, e of x goes to 0, and in the other case, e of x goes to infinity. Okay, but remember that this n to the power minus 2 by 3 is a very, very small thing. Okay, this is like 1 over a poly in n. Okay, so there's a very, very small probability. That's why I said, if it's a constant probability and all, ex will go to infinity. They all fall this side. Okay, whereas if you have something like p equal to 1 by n, then that falls in case 1, where the expectation will go to 0. That's the trick. Okay, if you're not familiar with this kind of growth functions, please try to imagine how a plot of this will look like. Try to plot n to the power minus 2 by 3 as a function of n. Okay, but so we have a nice idea about expectation. Expectation seems to kind of show a phase transition kind of a behavior around this function, right? So if the probability is little o of a particular function, expectation is 0. If it is little omega of the same function, its expectation is infinite. But we were not after the expectation, right? Expectation was only a tool that we used. What we are after is the probability that G contains a copy of K4. This is where our bounds, Chebyshev bounds and all may come in handy. So this is what we want to analyze. What is the probability that xs is greater than or equal to 1? Okay, why do we analyze probability that xs is greater than or equal to 1? That is because this is exactly the probability that G contains K4. Think very, very easy, very easy, almost by definition. Xs counts the number of. Okay, again, why did I put s? Should have been just probability that x greater than or equal to 1. Okay, the some random variable greater than or equal to 1. This x counts the number of K4s. So if it is at least 1, then that means G contains a K4. So x greater than or equal to 1 is the same event that G contains a K4, and this is the probability that we want to analyze. So the case 1 is easy. That is when E of x goes to 0. That's when P of n is little o of n raised to minus 2 by 3. Okay, so if you are this is your n, like let's say your n raised to minus 2 by 3 might go something like this. This is your n raised to minus 2 by 3. For something that goes faster than that, this is some function, this is the P of n we are talking about now. For such functions, your E of x, as we already saw, goes to 0. But now Markov inequality will give us this probability, or a bound for this probability that x greater than or equal to 1. This 1 I can write it as 1 by Ex times Ex, right? 1 is equal to, and hence by Markov inequality, by the way, this is a positive random variable because it's or rather a non-negative random variable because it's a counting random variable. Hence, and it has a finite expectation. We in fact know that it tends to 0. So in this case, we can apply Markov's inequality. In the second case, we cannot because expectation goes to infinity. Since so the premise for Markov's inequality is there, and it gives you 1 by this constant, which is okay. I had already written this here, which is by Markov's inequality at most E of x, and this upper bound tends to 0, which means since probability is a positive quantity, it is sandwiched between 0 and an upper bound which goes to 0. So this probability also goes to 0. Equivalently, the complement event, which is the probability that x equal to 0, or this is same as which event? This is same as the event that G does not contain a K4, in which case we call it G is K4 free, or we can even say that the clique number of G is strictly less than 4. Omega of G is the size of the largest clique, that is less than 4. This is all the same event. The probability of that event tends to 1. Okay, so if P is this small, if it is little o of n to the power minus 2 by 3, then the graph is almost surely, in fact, the correct word for this is asymptotically, because it's a limiting statement, not asymptotically, almost surely K4 free. Okay, so if you have a probability that goes to 1 as n tends to infinity. By the way, here we are not working with, we started off with a particular GNP, but when you take the limit that n tends to infinity, we are no more talking about a particular random experiment. We are talking about a sequence of random experiment with n increasing each time, and we are saying that in this sequence, the probability that G contains a copy of K4 tends to 0. Right? Yeah, that event tends to 0 provided P is less than or P is little o of n to the power minus 2 by 3. Okay, so this asymptotically is because it's not for a fixed n, but because n goes to infinity, and almost surely is because you can pick any epsilon, and because of this limiting behavior, you can have this probability as close to 1 as you want, greater than 1 minus epsilon for any epsilon that you choose. Okay, this is abbreviated usually as asymptotically, almost surely. Okay, so this is not the first time we are seeing this trick of first analyzing doing all your probability computations with a fixed n, getting it into a function of n, and then taking the limit as n tends to infinity. We have seen this in the Hardy-Ramanujan case also. Okay, yeah, so this is the conclusion, at least in case 1. If Pn is little o of n to the power minus 2 by 3, then a graph G sampled according to Gn comma Pn is almost surely K4 free. Okay, now let's analyze case 2, where Pn is little omega of n to the power minus 2 by 3. So now your Pn will look like this. Okay, this is Pn for case 2, and this is Pn for case 1. Okay, so yeah, so I mean, this I had already said, when you say a function f of n is little omega of g of n, that essentially means, or by definition, it is limit fn by gn tends to infinity. And hence, you can easily verify that E of x tends to infinity as n tends to infinity. If you want to, I mean, if you are confused about that, you can do the details here. Okay, because this Pn, what is written here, Pn is equal to omega n to the power minus 2 by 3, by definition means this. Okay, and now if you do a proper rearrangement of terms and take a correct power, you can show that this n to the power 4 p power 6 of n goes to infinity. But what does that say about probability of x is equal to 0? Okay, so you have a random variable with an infinite expectation, but we have seen examples that does not mean the probability at x equal to 0 is small. Okay, you can even have a random variable which is 1 with probability 1 minus 1 by n and n with probability or let's say n squared with probability 1 by n. What would be the expectation of x? Expectation of x would be 1 into or 0 with probability. So 0 into something, 0 into 1 minus 1 by n plus n squared into 1 by n, which is equal to n. So I can now choose n to be as large a number as I want. Don't get confused. I should have used probably instead of n, I should have used some m maybe. Yeah, this has nothing to do with this n we are using here. M squared. So m, yeah, right. So you can pick your m to be arbitrarily large, and you having a large expectation does not mean the probability at 0 is small. Okay, so in order to say something about this, we need a concentration bound. Okay, like in some sense we have to contain the variance and then apply the Chebyshev bound. So if we can show that, okay, so but here again calculating the exact variance of this x is going to be very cumbersome, so we will only estimate x. And before embarking on this task of estimating the x, it is better to know estimating the variance of x, sigma x squared. It is better to know what is that we need in order to bound this probability of x is equal to 0. Okay, so if you know that, then that means we can be a bit loose with the estimate and avoid extremely detailed calculations. So what we need turns out to be exactly this. We want to show that the standard deviation, not the variance, the standard deviation is little o of mu of x, or equivalently the variance is little o of mu of x squared. Okay, this is our target. If we can show this, then we are done. So let's see why. Okay, this we have already seen 2 classes ago, but let me quickly recall that. Okay, so by definition, what does this mean? This means that the sigma x by mu x as of goes to 0 as n tends to infinity. Okay, so what is, you don't see any n written here, but ideally, I mean, I'll just write it once, but then in order to avoid the clutter, I won't keep doing that. Ideally, these are functions of n. Why? Because x itself is a function of n. Okay, so it is in that sense that this expression makes sense. Okay, so as you increase n, what happens to the ratio of standard deviation to mean? If we can show that that goes to 0, then we can show that probability of x equal to 0 is small. That is like your random variable is kind of something like this. Okay, it kind of avoids 0, and probability at 0 approaches probability that x equal to 0, which is probability that g is k4 free, approaches 0. How do we get from this to this qualitative statement? By Chebyshev, probability that x is equal to 0. Chebyshev will come here. So first I'm just massaging this event. This actually we have seen this once before, so it's repetitive if you already remember that. Probability that x is equal to 0 is at most probability that x less than or equal to 0. So this is your e of x here. Remember, e of x tends to infinity, but for any finite n, e of x is finite. Okay, so I can resort to this picture. Okay, so now if x has to be equal to 0, x has to be here, which means its deviation from the mean is at least e of x, or at least this is also equal to mu. Okay, at least mu x. Okay. So yeah, so that's what you finally arrive at this point. Probability of x equal to 0 is upper bounded by, so in order for x to be 0, x has to deviate from its mean by at least the mean. Okay, so that's ready to, this is the form in which you can use the Chebyshev inequality. Mu x, you can write it as a constant times sigma x by multiplying and dividing by sigma x. So mu x by sigma x is the constant. The reciprocal of that is the upper bound given by the Chebyshev inequality, which is sigma squared x by mu squared x. And this is what we have, we are trying to show that this will tend to 0. Okay, this is exactly the definition of saying sigma x equal to little o of mu x. Okay, so recall, from this point onwards, our task is limited to showing this relation. Okay, let me number this as 1 or something. Our task is limited to showing that the standard deviation of this random variable is little o of the mean of that same random variable. Okay, so the standard deviation grows asymptotically, grows at a rate which is slower than the rate at which mean grows. Okay, now it's a very intuitive picture, right? If your standard deviation is growing faster than the mean, then even though the mean is kind of increasing, your tail may be significant at 0. Okay, but if your standard deviation is going at a rate slower than the mean, then you expect almost 0 probability at x is equal to 0. So that's what we have already shown. So we only have to now prove this claim for this particular random variable or the particular sequence of random variable, that this goes to 0. Okay, so let's get to that. So this is the claim we are trying to prove under this case 2 regime, where P of n is omega n to the power minus 2 by 3 and G is sampled according to Gn Pn. It almost surely contains a K4. Okay. Oh, yeah. I mean, I should have just said x goes to, I don't know why I wrote this general claim here. What I wanted to say was that now what is left to prove is sigma x is equal to little of mu x. Okay. So, okay, that I have written here actually. Okay, I have said that it is enough to show that sigma x is equal to or sigma squared, because variance is easier to analyze. So maybe we'll directly analyze the variance rather than sigma x. Recall that x is the sum of n choose 4 random variables. Each of these x's was a Bernoulli 0, 1. Hence, its probability was p power 6. So yeah, but first let me write it down. The whole expansion of sigma squared x, it would be the sum of the variances, these are the diagonal terms, plus sum of all the covariances between distinct sets S and T. Okay, so this is a standard formula for covariance, right? You can verify that. Try to verify this by taking expectation of x minus mu x the whole squared. Your x is sum of write x minus mu x as sigma x1 minus sigma xi minus mu I the whole squared. Take its expectation. Treat these guys as individual terms. Don't expand this. Call this as yi maybe, and then you'll be able to prove this formula. But do that as an exercise if it is not obvious to you. And so it has two terms, the variance term and the covariance term, as I would call it, TV and TC. Now TV is easy to analyze because the variance of each individual term is p power 6 times 1 minus p power 6. In fact, the variance of a Bernoulli p is p into 1 minus p. But here p power 6 plays the role of p. And this sum contributes how many terms? N choose 4 terms. But instead of doing this exactly, since again here is the point I mentioned earlier, keep in mind that we are not interested in calculating the variance exactly or even estimating it accurately. We are only interested in proving this result, that variance is little o of mu squared. Okay, so all these approximations are justified. You can upper bound this 1 minus p power 6 by 1. So this becomes a sigma over p power 6, which is nothing but the variance. Which is nothing but the expectation of x mu x, right? So it is enough to show that this term is little o of mu squared. So if you can quickly show that it is little o of mu, then it is at most mu, then this is little o of mu squared. Remember that this mu and all is an increasing function. So don't think that mu can be smaller than 1 and whether this would mean TV is less than mu squared. This is a large function, so this is a little o of mu x squared. Okay. Yeah, so our time would be spent mostly in analyzing TC, the cross terms. Okay, so again, it's very easy to verify that the covariance between two guys, XS and XT, which by definition is E of XS minus EX times XT minus EXT. This is the definition of covariance. This is the definition of covariance between XS and XT. If you expand it out, you will get 4 terms, but 3 of the terms are going to boil down, are going to be, after you take the expectation inside, all the 3 terms would be EXS, EXT with appropriate signs, which will finally give you a -1. It's a standard exercise. Okay. But okay, now among all actually we are struggling because not because of any individual covariance term, we are struggling because there are so many things that we have to add up. There are quadratically many. By quadratic I mean quadratic in n choose 4. There are n choose 4 choices for S and n choose 4 -1 choices for T. So there are something like n to the power 8 choices or terms that we are adding up, and that is what we are really worried about. Okay, but an easy observation will tell you that among these S and T's, some of them are independent, right? So for example, if your S and T were disjoint sets, okay, this was your S and this was your T, then we know that XS and XT are independent. The fact that this induces a K4 has nothing to do with whether T induces a K4. So in which case, if they are independent, then your EXS XT becomes EXS times EXT. Okay, expectation goes inside a product if there is an independence, and this cancels out with this. Okay, so whenever S and T are independent, this is okay. By the way, S and T are independent even if they share one vertex in common, because this event only depends on edges, whether some edges are present. So even if S intersection T is 1, there is an independence. So the only case that we have to consider is when S intersection T is either 2 or 3. That's the only case when XS and XT will have a dependence. Why did we not consider S intersection T equal to size is equal to 4? Because then S and T are the same sets, but that is anyway not there even in this summation. This summation is only done for S not equal to T. Okay, so from this point onwards, there's a major change. That is why I have highlighted in red. Instead of analyzing S not equal to T, instead of summing up over all pairs of the summing random variables, we are only summing up those pairs where there is some dependency. Okay, so this S tilde T is a shorthand to denote that S and T has some dependency. Okay, so we are now adding up as many terms. Okay, here actually I should have written this minus EXS EXT as one step, and then since I'm only looking for an upper bound, so actually if I write this, then this is an equality. Okay, if I write this, then this is an equality. I'll write this extra step here, and then I can upper bound that by sigma S and T dependent E XS XT. Okay, because this is a negative term. Why is this a negative term? EXS is positive, EXT is positive, so this is a negative of a positive times positive. So this upper bound is valid. Okay, so now what is expectation of XS XT? So XS is an indicator random variable. It's a 0-1 Bernoulli. This is also a 0-1 Bernoulli. Now the product of two 0-1 Bernoullis is also a 0-1 Bernoulli. Right, because product of a 0-1 random variable with another 0-1 random variable can only be a 0-1 random variable. Hence, this is an indicator random variable, but of which event? So this will be 1 if both XS is 1 as well as XT is 1, or equivalently this is 1 if both S as well as T. Okay, I mean these pictures are misleading because those pictures don't come up here because we are only analyzing those pairs. So let me draw one example where there is some dependency. Yeah, so these are the two cases where there is some dependency, right? So imagine one of these cases. So XS XT will be 1 if both XS as well as XT is 1, which means in this case 6 plus 6 minus 1, right? All the 11 edges or so, right, are there, and in this case, yeah, 3 plus 4, maybe 7 edges, all of them are what? Okay, so that is the expectation of this. Okay, now this is a intersection of events, or I can write it as a conditional times a marginal probability of x is equal to 1 given xt equal to 1 times probability that xt is equal to 1. Okay, so now this is, by the way, a double summation, because you vary s as well as t. I split it into two summations. I'll run t over the entire choices, okay, entire and choose 4 sets, and then pick all those s's which depend on that particular t, which have an intersection of size 2 or 1 with that t. Those s's alone I will pick. So yeah, here it is still S intersection t, and then from this summation here only, since t is kept constant, I can pull out this term from this summation. Now we are going to make use of a symmetry argument. Okay, so look at this inner summation, probability that x of s is equal to 1 given xt is equal to 1. Okay, so s is a running variable, that's a summing variable, but at the face of it, this looks like it depends on t. In a general context, if you write x as a sum of variables, it will depend on t. But in the problem that we are studying and many other similar problems, this is very symmetric in the sense that no matter which 4 set t you pick, okay, no matter which 4 set t you pick, now you sum over all the s's that depend on it. This is symmetric in the sense whichever t you pick, this list of events and their probability is going to be the same. Okay, there is a very formal way of putting it down as a definition, but I'll not resort to it. I'll just maybe mention it in passing. This says that we can relabel the domain so that the new t becomes the old t, and by this relabeling, none of the interesting events changes their probability measure. Okay, so these are called measure preserving bijections of the sample space. Okay, so if you can do a relabeling of the sample space such that with one t1 you analyze this scenario, and with the different t2, if you want to analyze the scenario, if there is a measure preserving transformation which maps t1 to t2, then it is easy to see that all these probabilities are going to be the same. Okay, so please pause and think what we are saying here. The only thing, I'm not calculating this quantity, I'm just saying that this quantity is going to be the same for every t. Okay, that's so in general, this quantity, let's say nu, is a function of t, but it's going to be the same for all t, and hence I'll decide to just call it nu x, or I could have just called it nu. You will see why I call it nu x, because it's anyway related to x. Okay, so this is a symmetry argument. Now, since this is independent of t, I can pull that nu x outside of this summation and write it in this way. Okay, so this is now simplified to nu x times sigma over t probability of xt equal to 1. This is something which we know, right? This is probability of xt equal to 1 is e of xt, and summation over all t e of xt is your mu x, e of x, right? So this we could upper bound tc by nu x times mu x. Okay, now if we can show that this nu x is little o of mu x, okay, so this is this is little o of mu x, then this whole term would be little o of mu x squared, right? If nu x is equal to little o of mu x, then this whole term mu x is equal to little of mu x squared, and that's all we want. Okay, because we only want to show that the variance is little o of mu squared. TV we already saw is little o of mu squared. If we can show that this is also little of mu squared, this is sum of two little o of mu squareds, which would be a little o of mu squared. Okay, so now our aim is now to show that nu is little o of mu. Okay, so let's try to show that nu is what this guy is, right? This is the definition of nu. So this is for any particular t, okay, when the expression involves t, but by that symmetry argument, the t does not play a role. Every t will give you the same value, but still, in order to define that, we have to fix a t, and then vary across all those s's which are dependent with t, which means it has an intersection of either 2 or 3 with the set t. Both S and T are four-size sets, don't forget that. And probability that x is equal to 1 conditioned on the fact that xt equal to 1, or equivalently, this is a probability that S induces a K4 given that T is inducing a K4. So let's split the summation into two pieces, because S depends on T, the dependency can be of two types, when they share two vertices and when they share three vertices. Okay. So when they share two vertices, what is this conditional probability? You are given that the 6 edges which are among the T vertices, these green edges are already there. Now this will be 1 if the remaining 5 edges, these red dashed lines, they are there, right? So this is p power 5 is the probability. In this case, when they share 3 vertices and all the 4 edges in all the 6 edges in T are present, there are only 3 more red edges remaining. If they are all present, then excess is also a clique. So this happens with probability p cube. And now what is the summation? How many S's are there such that S intersection T is equal to 2? Simple combinatorial argument. From T, you can pick any 2 to be this sharing pair that you can do in 4 choose 2 ways. And then the remaining 2 vertices, these 2 vertices, you can pick among the remaining n minus 4 vertices. So that gives you n minus 4 choose 2 choices times this p power 5. When it comes here, you have this T already fixed. You can pick 3 of the 4 vertices in 4 choose 3 ways, and this remaining 1 vertex you can pick it to be any of the n minus 4 choose guys. Okay. Now let's only work with the ignore all the constants. This is like n squared p power 5. This is like n times p cube. Now it's only a matter of simple analysis. Okay, the structural analysis is over. Now it's only a matter of a simple analysis to show that this is indeed little o of mu. Okay, this is indeed little o of mu. One way to show that would be kind of write the expression for multiply and divide each term so that in the numerator looks like the expression for mu of x. Okay, n power p power 6 by n squared p, which will give you this will give you, right? So the numerator is already mu of x, and now if you can show that the denominator goes to infinity, then this is little o of mu of x, right? So yeah, why? Because if you take the first denominator n squared p, remember p we are in case 2, so p is omega to the power omega n to the power minus 2 by 3. Take the n squared inside, so this is 2 minus 2 by 3, which is n to the power 4 by 3, that tends to infinity. So this denominator here, this tends to infinity as n tends to infinity. Similarly, this denominator here, n cube p cube, p again is n to the p again is n to the power sorry, it was correct. Okay, it was n to the power minus 2 by 3 cube, so it is n to the power minus 2. So this is this is omega of n, and hence it tends to infinity, right? So this also tends to infinity. This is equal to mu x. This is also equal to mu x. So this is mu x by a term that goes to infinity, and hence this whole term is little o of mu x. Okay, so that's it. Okay, so we finished our proof. We have shown that the variance is little o of mu squared, and hence the concentration is there. So the probability that x is equal to 0 will go to 0. So if you summarize this as a theorem, this is what we get. If G is sampled from G n comma Pn, then the probability that G contains a K4, or equivalently the probability that the clique size of G is at least 4, tends to 0 if Pn is little o of this function. Let me call this is usually called as a threshold function when you get such a phenomenon, and it is 1 if Pn is it's an omega of this threshold function. Okay, so you see that there is an abrupt jump, from the probability, from almost surely being K4 free, it has suddenly jumped to almost surely being containing a K4. this abrupt transition is what is called as a phase transition. This is very similar to phenomenon in physics where, for example, ice does not gradually become water starting at some -5 degrees and ending at +5 degrees. At some particular temperature, it abruptly transitions from one phase to the other. A similar, in fact, there are models of random graphs called percolation models and all, where this is studied in a context which is closer to what is actually happening in ferromagnetism, this solid to liquid transitions and so on. You can search for it. It's a very fascinating area. And this function at which this transition occurs is called the threshold function or the threshold probability. Different properties may have different threshold functions. Okay, so G is almost surely K4 free if Pn is below the threshold, and almost surely contains a K4 if it is above the threshold. I should have actually said asymptotically almost surely in both places. Yeah, and this is the phase transition. And this above method of using this nu x, okay, using the symmetry, first of all converting it into a conditional probability sum and then using the symmetry and extracting out is very general, so that Allen and Spencer actually puts it down as a corollary. That's what, okay, I put it down as a theorem. Okay, I don't know why. So if let x1 to xn be indicator random variables corresponding to some events a1 to an, and let x is equal to x1 plus xn. Suppose we have ex goes to infinity and there is the symmetry among x1 to xn. Okay, the symmetry we have already discussed in detail, which says like any two different random variables can be mapped to each other by a measure preserving transformation of the domain. Okay, and if you can show that your nu x, which is defined this way, where you sum over, pick any, fix any I, and then j is a running variable, but this I, the choice of I is important to write this expression, but it does not affect its value because of the symmetry there. So fix any I and now calculate this sum where you sum the probability of aj given ai, but only for those j which depend on I. Okay, only for those j such that aj and ai are dependent. Otherwise, this would be probability of aj, but don't add them. Okay, if you add them, it will grow. But our aim is to show that this is little of mu x. If all these three conditions are satisfied, then x is greater than 0 almost surely. Okay, it's away, the concentration is good enough so that the tail at 0 vanishes. Okay, in fact, you can say more. You can actually use Chebyshev inequality with some epsilon times mu x rather than mu x as we did, and show that you will pay this additional price of an epsilon squared in the denominator, but in an asymptotic analysis, any constant in the denominator or numerator, does not matter. It will still go to 0. So this means x is very concentrated around E of x, provided this nu x is little o of mu x. Okay. Now, yeah, I don't have time to go to the next application. I wanted to talk about a SAT phase transition to emphasize the fact that this phase transition is not just a phenomenon you see in random graphs. You see it in a varied context across combinatorics, computer science, graph theory, everywhere. So, or maybe I'll not do all the calculations in detail. I'll take maybe 5 minutes and at least tell what is the problem. Anyway, here we do not have a complete answer. The threshold for this is still an open question. We only have partial answers. So let me quickly go through this. So here, what is the random object that we are sampling? We are sampling an E3 SAT. Okay, so remember E3 SAT is a CNF formula in which each clause has exactly 3 literals, and all the 3 literals have to be of distinct variables, right? It should be something of the form x1 or x2 bar or x3. Something like x1 or x2, 2 variable clauses are not allowed, or even things like x2 intersection, x2 or x2 bar, this is not allowed. Okay, so these are the exact 3 SAT formula. We have already seen it in one of the early lectures. Now the random experiment is picking a E3 SAT formula with n variables and m clauses uniformly at random. Okay, n variables and m clauses uniformly at random. How do we do that? There are how many such clauses possible? Each clause involves 3 variables. Since you have n variables and you have to pick 3 of them, you can do that in n choose 3 ways. And for each of the 3 variables, you have a choice whether to retain it in the positive form or to put a bar or to negate it. Okay, so that gives you 8 choices. So there are 8 times n choose 3 potential clauses. You pick one uniformly at random and repeat this independently m times. Okay, so yeah, that is why we have this. The independence is between clauses. Okay. By the way, there is also an independence between the negation or not negation within a clause. That's also important. Okay. So this probability distribution we will denote by some script phi of n comma m. Let's call the variables to be x1 to xn, and phi of n. Actually, this random experiment you can also do it in 2 stages if you wish. First by picking this. In fact, that's how I described it. First by picking the 3 variables and then negating them with probability half. Okay, what is the question we are interested in? What is the probability that formula created that way is satisfiable? Okay. Right, so we have to now analyze this in terms of random variables. So what would be the natural counting random variable to put here? It's a binary question, is it satisfiable or not? But we have seen that studying expectations of counting random variables are easy because they are more likely to be expressible as a sum of indicator random variables. So here the natural thing to count is the number of satisfying truth assignments. So remember, a truth assignment is nothing but assignment from this variable set to t or false. Okay, so you can set each of the n variables x1 to xn as either true or false. That's what is known as a truth assignment. And for each truth assignment, we will define a random variable. Each truth assignment t, we will define a random variable xt, which is 1 if t satisfies this formula phi, 0 otherwise. So your what would be E of xt? What is the probability that a particular truth assignment will satisfy this clause? So remember, the randomness is not associated with the truth assignment. The randomness is associated with the selection of phi, the choice of phi. So for this xt to be 1, each of the m clauses have to be satisfied because it's an AND of clauses. But for each clause to be satisfied among the 3 literals, even if 1 is true, it is satisfied. Okay, so which means there is 7/8 probability of one clause being satisfied. That's very huge. That's a good number. There's only 1 in 8 chance that it might actually be not satisfied. That's when so it is something like in this example here, the only case it won't be satisfied is when x1 is equal to true, x2 is equal to false, and x3 is equal to false. Out of the 8 cases, this is the only time it will be bad. So you have 7/8 probability of satisfying one clause, which is a good number. But since you have to satisfy each of the m clause, the probability dramatically goes down to 7/8 to the power m. This will be very close to 0. It's a very small probability. Why could I put a power of m? Because the choice was independent. Okay. Now, what is your counting random variable x? It's just the sum of xt. This will count the number of satisfying assignments for phi. How many xt's are there? As many truth assignments as you can build, which is nothing but, since you have n variables, you have 2 to the power n such things, right? So your expectation of x is 2 to the power n times 7/8 to the power n. Now remember, the event that phi is satisfiable is equivalent to event that x is greater than or equal to 1. There is at least one satisfying assignment. That's the definition of phi being satisfiable. So now it's only about rearranging this term. This 7/8 to the power m, I can write it as 2 to the power log to the base 2 of 7/8 the whole power m, or which would be this one. Do a calculate log 2 to the 7/8. It will be minus 0.193. Okay, now what about this number? When does this Ex become very small? Like it will go, when does it go to 0? When does it go to infinity? Right? So this is less than 1 if this guy is less than 0, which means your 0.193 m is more than n, or equivalently m is greater than 5.2 n, and this Ex is greater than 1 if m is less than 5.2 n. Okay, so this is, first you should pause and make an intuition here. If there are more clauses, then the expected number of satisfying assignments is very small. It's intuitive, right? That is intuitive. If there are fewer clauses, then the number of satisfying assignments are expected to be more. But in order to now take our limit as n tends to infinity, I don't want to carry two free variables f, m and n. I'll tie them together by this relation. Okay, I'll just bother about the ratio of m by n. Okay, your r is nothing but the ratio of m by n, and then I can my model would be this n comma rn, and then I can take n to infinity. That's the idea, right? Okay, so if m is equal to Rn and this R is greater than 5.2, then you can substitute that here and then see that you will get something like 2 to the power negative constant times n. So this expectation goes to 0. And by Markov's inequality, case 1 is like the easy case, right? By Markov's inequality, this probability is bounded by E of x, that also goes to 0, which means almost surely this clause is not satisfiable if you have more than 5.2 times the number of clauses is more than 5.2 times the number of variables. In the other case, unfortunately, unlike in the or it's nothing fortunate or unfortunate, it's just a fact of nature that the variance is very large, that you really cannot use the Chebyshev bound in this range. In fact, you will not be able to show that sigma squared is little of mu squared. And empirically, people have studied it and they know that this 5.2 is not the real threshold. What is conjectured is that the threshold is somewhere around 4.2 based on experiments. So people believe that if you do such a random experiment with r less than 4.2, you get a formula that is almost surely satisfiable. If it's above 4.2, it's almost surely unsatisfiable, but it's still a big open question as to theoretically proving this bound. Okay, this is still not found, but certain similar questions have been studied, like exact threshold is known for a variant of this called 1 in k sat and so on. By the way, this is not a theoretical exercise alone. There are these SAT solving. SAT solving is a very important computer science question. We know that it's an NP-complete problem, and hence heuristic algorithms which can be faster than the previous best known algorithm. This is a perpetual ongoing competition. Every year you have better SAT solvers because they form the backend. They form the engine by which most combinatorial optimization problems which are NP complete are attacked. Okay, so if you are ready to do exponential algorithms, you can do it very efficiently if you can solve SAT efficiently. So there are these very famous attempts at solving SAT faster and faster. But now, how do you, since there is no theoretical analysis is not what is needed here, you have to give benchmark SAT problems. And no human being can write down SAT problems of such huge size. So they are generated automatically. And this is a very naive probabilistic model to generate random SAT instances, right? But if you generate this random SAT instances with a number of clauses m much less than 4.2n, then these are going to be easy no instances for the solvers. And if you generate it with much more than 4.2n many clauses, then it's going to be an easy yes instance for the solver. So all the tough instances really lie in this phase transition region. The tough SAT problems are when water turns from ice to H2O turns from ice to water. It's so if you look at many of the SAT solving benchmark questions available in the net, the number of clause to number of variable ratio will be around 4.2n. But nowadays there are slightly more advanced probability distributions by which SAT solver benchmarks are generated. They put in some extra conditions to make it a bit harder. Okay, so yeah, this is about a general template to attack the covariance terms, and more importantly, an introduction to this area of phase transitions. In fact, Alon and Spencer devotes one full chapter on this phase transition, but in the interest of time, we will have to stop this discussion here. In the next class, we will see maybe an application of Chernoff bounds. Okay.